Okay, so let's see. I want to talk about the Allard theorem now. So we're going to be looking at stationary variables. So as usual, U is open in some Euclidean space Rn plus k. And let's assume that we've got a stationary rectifiable varifold. In this set U, actually, it's really more general. It's okay if this varifold, instead of being stationary, it's okay if it's merely got mean curvature, generalized mean curvature in LP for P bigger than N. But a bit pointless to actually complicate the proof with that, because the ideas of the proof are exactly the same and every step of the proof is exactly the same. Just have to be a bit careful about carrying along this mean curvature. So I'll just mention that it's okay if V has generalized mean curvature instead of being stationary. H in LP, P bigger than N. But it's not worth complicating the argument because it'll just obscure the main ideas if we try to do that generality, and nothing really changes. So let's stick to the simplest case, stationary. So remember that means integral over M div sub M tangential divergence d mu equals 0. Here I'm going to be using mu equals mu sub v, which remember is just Hn restricted to the density function. In other words, d mu is just theta dHn. And let's do a preliminary lemma first. There's a couple of important quantities that we need to introduce. One is the so-called tilt excess. So here T is going to be any n-dimensional subspace, linear subspace. Of Rn plus k. And the tilt excess that's defined to be, it's this quantity, integral sigma to the minus n. This is the tilt excess over a ball. V sigma centered at some point xi contained in U. And this is the integral over the ball. It's got this normalizing factor, that's the natural scaling factor to make everything scale invariant. And then in here you have the difference between the orthogonal projection onto the approximate tangent space minus the orthogonal projection onto this given space, T, and you square it, and you integrate. So you see what this is. This is what the physicists would call the mean square deviation of Ptx, the tangent space away from the given tangent space T. Mean square deviation. Of Tx away from T. So notice, of course, it's only 0 if Txm coincides with T everywhere, almost everywhere at least. So that's the first quantity, and then there's the height deviation. That's sort of similar, except it's still got a normalizing factor at the front. But this time, we're integrating the distance of a point x in the support from t. And you're taking the square of that. Of course, you've got to normalize it by sigma. It wouldn't be of any use to us if we didn't divide by sigma. After all, the ball's radius sigma, so obviously the distance of any point inside the ball is less than sigma. So the important quantity here is the ratio. Distance of x from the subspace compared to, except that this is supposed to be the affine space passing through the center point of the ball. So this is important. This is, instead of t here, we take the affine space, psi plus t. And we're squaring that d mu. So the picture for that is that here's m, or support mu, better. And here's the point xi. And this time, and this is the radius sigma, this time we're measuring that height there compared to the ratio between that height and the radius sigma. So again, this is a mean square deviation. This time it's the mean square deviation of the height away from the affine space. So this is the space xi plus t. Of course, the origin's down here somewhere, and t goes through the origin, but we're talking about the affine space here. So they're two extremely important quantities, and they'll play a big role in the proof of Allard's theorem. Now, there's a nice preliminary lemma that relates these two. If you take a ball, any ball, let's call it y. I'm going to usually, it should be consistent here. I'm usually going to be taking center points called y, so let's start off with that since we're going to be doing that. So this is the point y, and then this is y plus t. Right. So the preliminary lemma relates these two. So suppose that you've got a ball contained in the set U, and gamma at any number between 0 and 1. Then the integral, then the tilt excess over a slightly smaller ball, that is, you take the ball radius gamma rho rather than rho, centered at the point y, but it's still the tilt excess, so we're still doing the mean square deviation away from t. So here t again is any given subspace, any n-dimensional subspace, linear subspace. Then this is less than or equal to a constant depending only on, by the way, this constant that I'm writing here depends only on the dimensions n and k. We're in Rn plus k, and our manifold is dimension n. So this constant depends only on n and k. Today, throughout the lecture, anytime I write c, it's got to be a constant that depends only on n and k, right? It might be the same constant. It may change from line to line, but it's always a constant that depends only on n and k. Less than c times this other guy, this one. Sigma to the minus n, integral over b. Oh, right. Sorry, that was dumb. Let's stick to the same notation. Let's call the radii sigma. So it's sigma to the minus n, but this time we're shrinking the ball slightly. And then it's sigma to the minus n, and again the full ball, b sigma rho, and then it's this guy. Distance of x to y plus t over sigma squared d mu. Of course, the variable of integration, I should have made this clearer. The variable of integration here, x is the variable of integration, d mu x. So we're integrating the height over the entire support, the distance from the affine space. Yes? Okay, but you see, yeah, I know, but let's suppose, okay, let's take this in half, and then it's constant, right? The important cases of this, of course, are when gamma is close to 1, because if gamma is closer than 1, that includes all the cases when gamma is a lot smaller, right? So we may as well assume gamma is between half and 1. Then there's no dependence on gamma on the right side. Oh, but there is a dependence on gamma, actually, on the right side. So this is C. I painted myself into a corner. I said this C is only allowed to depend on n and gamma, and I've immediately violated that principle. So let's not do that. That's that. So I claim that. Notice that blows up as gamma tends to 1. So you can't let gamma equal to 1, of course. It doesn't work. Okay, so let's give the proof of this. Okay, yes. So without loss of generality, we can assume that y equals 0 and t is equal to Rn cross 0. You can always just make an orthogonal transformation of everything. Oh, notice all these quantities are invariant when you do that, so that doesn't change anything. So let's do that. And then it's the old story. I claim that you can prove this just by making a particular choice of x in this identity. We've got a bit of mileage out of that before when we were talking about the monotonicity identity. We made a particular choice of x in that identity and got some interesting results. So we're going to do that again. So we've got to work out what the right choice is. So I'm going to choose x at a point x. Well, I've got to make sure it's got compact support. So let's remember this is for every x, which is C1 with compact support in U and with values in Rn plus K, the usual situation. So we've got to respect the compact support thing. So let's take care of that right away. Take that to be zeta of R, where R is going to be just mod x, the length of x, and zeta is a function that looks like this. So I'm going to draw the graph of zeta here. The graph of zeta. It's identically 1 until you get past radius gamma rho, gamma sigma. And then it goes down to 0 smoothly before you get out to radius sigma. Like that, and symmetric. Same thing on the other side, like that. So this is height 1. So the usual kind of cutoff function. So that takes care of the compact support. Now I've got to tell you the direction. Now remember, when we were proving the monotonicity formula, we took direction x, the radial direction. Now, instead of taking direction x, we take the first n components 0, and the last k components we take to be xj. J equals n plus 1 up to n plus k. So this is xn plus 1 up to xn plus k. Like that. And now we've got to compute the divergence. Okay, so that's, remember, if we let Eij be the matrix of the orthogonal projection onto the approximate tangent space, of the approximate. So this is the matrix of the orthogonal projection onto the approximate tangent space. It's an n plus k by n plus k matrix. Symmetric. And let's see, let's do the div of this part first. Well, notice that's just, remember the general expression for the divergence is sum from ij equals 1 up to n plus k of Eij dixk. Oh, that's bad. Eij dixj. That's the general expression, remember, for the tangential divergence in terms of the orthogonal, in terms of the matrix of the orthogonal projection. And notice that xj is 0 for j equals 1 up to n, and di of xj is equal to Kronecker delta ij for the last k components here. So this just reduces to a double sum. So we've got to differentiate this bit, so let's do the zeta bit in a minute. So the zeta r bit, let's leave that for a second and do the this bit. Well, as I say, you get Kronecker deltas from here, and the first n components is 0, so you just get a double sum. J equals 1 up to n. Since you get a Kronecker delta ij, the double sum becomes a single sum, and it's j equals n plus 1 up to n plus k. Ejj. And then we've got to do the zeta r bit. So that's zeta primed r times grad mr dotted with this vector. Let's call that x prime. The last k component, let's call those x prime. Okay, so that's what we get. Now, Ejj, notice that, let's work this out in the case when, let's work out this quantity in case when t is, as we're assuming in this case, we're assuming t is Rn cross 0. So what's Ptxm minus Pt in this case when t is Rn cross 0 squared? What is that? Well, that's just the sum of squares. This is just the length of the matrix, so this is just the sum of squares, Ij equals 1 up to n plus k, of Eij minus epsilon ij, where epsilon ij is the matrix of the orthogonal projection of this. So epsilon ij is a matrix that's got identity in the n by n slot here and there's zeros everywhere else. Like that. This is the n by n identity. So that's epsilon ij, and this is the sum of squares. Okay, so let's work that out. So we square this out, and remember this is a projection matrix, so when you square that matrix you get the matrix back again, except you get the trace of it now. Now the trace of an orthogonal projection, remember we've used this several times, the trace of an orthogonal projection onto an n-dimensional space is just n, the dimension. So here we get n, when we square this we get n. Similarly, so we get 2n minus the cross terms, sigma ij equals 1 up to n plus k, Eij epsilon ij, but that's just the sum from I equals 1 up to n, because epsilon ij is the identity in the first n by n bit and zeros everywhere else. So this is 2n, 2 times, minus the cross term, so there's lots of those. So it's 2 times n minus the sum, j equals 1 up to n, Ejj. But that's exactly, remember n is the sum of all the Ejj's up to n plus k. So this is exactly just twice the sum, j equals n plus 1 up to n plus k of Ejj. So that's nice. That's this thing. So this is, this thing is a half of this guy. So this is zeta r times a half times mod Ptxm minus Pt squared. And then we've got to do this thing. Okay. And this one is, this is this one is just the orthogonal projection. See, I can so this one is theta primed r, and I can put the orthogonal projection from there onto there. It's one of the properties. I mean, orthogonal projection self-adjoint operator, so I can put it onto the other thing. So this can be written as the full gradient of r dotted with the orthogonal projection onto Txm of 0x prime. Okay, and that's right. So that's some. Let's see. I don't really remember how this is supposed to go. I know what it's supposed to come out as, but I seem to be making a bit of a mess of that. Let's see. Yeah, so this is, okay. So this is, yeah. Okay, so it's, oh yeah, I see. So it's the sum, this guy is the sum, I equals 1, I equals n plus 1 up to, there's only the components n plus 1 up to n plus k here. So it's n plus 1 up to n plus k, and then the sum j over all the indices of, and dr is just xj over r, right? djr is just xj over r. So this will be theta primed r over times xj over r times xi. Okay, that's what that is. And times eij, the orthogonal projection, eij. Now, notice that this is the same as epsilon ij again. There it is up there. Epsilon ij is 0 if I is bigger than n, you see? So I can sneak in an epsilon ij here. See, that same thing, because it's epsilon ij is 0 for when I is n plus 1 up to n plus k. So I can do it that way. And so this is equal to a half theta r mod pt xm minus pt squared plus, well, let's start to estimate something. So it's less than or equal to then the absolute value of this, and the absolute value of xj over r, that's less than or equal to 1, and this is just less than r, so it's less than r times the sum ij equals 1 up to n. So I'm using Cauchy-Schwarz inequality here, so it's the square root of the sum of squares of these things. So by Cauchy-Schwarz, it's that. Notice this length of this vector is 1. Length of that vector is less than r, so we get an r there, square root. All right, so we looks like we've made some progress. So, right, so this is what we have. So we have this plus this. Oh, sorry. I wanted to keep this term by itself here, so I didn't want to do this as I've done it here. I want to say that this is bigger than or equal to a half minus that. I use Cauchy-Schwarz inequality in that way because this is the nice positive term. I want to keep that one. And this side is, and of course the whole thing is 0. So, okay, so let's do that then. So div, so let's use this identity now. We've computed the div, so let's use this identity now. So hence, 0 is equal to the integral of the divergence, which we just computed, is bigger than or equal to a half times that positive term, so it's a half times the integral of zeta r times mod pt xm minus pt squared d mu, and then minus this stuff. So I should put this stuff onto the other side. So I get, well, let's not do that yet. So minus mod z prime r times mod z primed r times square root of, now remember the epsilon, sum of squares of the epsilon, here it is down here, the sum of squares of these epsilon ij's is again just ptxm minus ptx. So this is just minus the first power, ptxm minus pt d mu. Okay, that's good. And now we just put this onto the other side there, and you see that, just use a Cauchy-Schwarz inequality, and you see that zeta, well, maybe I should have used zeta squared would have been better. In that case, we'd get a factor of 2, and there'd be and when we differentiate zeta squared, we'd get a factor of zeta. So this would be 2 minus 4 times zeta times r times zeta primed r times the first power, though, of txm minus pt. And yeah, so I see. I dropped an important term here. Notice that the length of this guy is the distance to the plane. So for I equals n plus 1 up to n plus k, length of I is less than or equal to the distance of the point x from the plane, t, because the plane is just Rn cross 0, and xi is the ith coordinate. So I've missed a factor here. This is supposed to be times distance of the point x to the plane, t, d mu. Now it's correct. So now we just use Cauchy-Schwarz inequality, and you see this tells us that zeta r squared ptxm minus pt squared d mu is less than or equal to this term, but I'm using Cauchy-Schwarz, so I can pull back zeta squared times that into this guy, and leave the rest on the right side. So we get a constant. Actually, the constant turns out to be 16 if you work it out, times the integral of zeta prime squared times distance xt squared. And I also forgot that there's no, that's right, zeta prime squared. That's correct. So we get that. And this is d mu. And now remember, our zeta is this thing here. So we can certainly choose zeta to satisfy this so that gradient of zeta is less than or equal to a constant over 1 minus gamma, because we've got to go from height 1 down to height 0 in a distance 1 minus gamma times sigma. So it's c over 1 over sigma times 1 minus gamma. So this zeta prime squared will be less than or equal to, let's just call it a constant. Again, we've got to agree to the convention. This means it only depends on n. C over sigma squared times 1 over 1 minus gamma squared times the integral of the distance squared, x to t du. So there we are. That's the lemma. Exactly this result. People that know a little bit of PDE notice that this is very similar to test function arguments in PDE when you're looking at divergence form equations like the minimal surface equation, and you're trying to estimate the gradient in terms of the height. this is exactly the sort of inequality that you use. Okay, so that's the first sort of a preliminary lemma, that you can always estimate the tilt excess in terms of the height excess. Very nice lemma, and it's very general. No real assumptions needed. Okay, and now let's talk about something more serious now. So we're trying to prove the Allard theorem, which means, and as I mentioned a couple of lectures ago, that is going to involve some sort of harmonic approximation, approximating the support of our varifold by the graph of a harmonic function. It's going to be what we're aiming to do. And the first step of that is to show that we can at least approximate it to, we can at least arrange to get a nice affine approximation to the thing. In fact, notice at the moment we don't have that. We have that the tilt excess is less than this affine distance, but we don't yet know whether we can make that small or not. So that's the first lemma that I want to prove. It's called the affine approximation lemma. I'm going to prove that under certain conditions you can make this small by choosing your affine space appropriately. Okay, so let me state that precisely. So there's going to be some blanket assumptions that we're going to be assuming now for the next 3 lectures, I guess. So I'm going to call these assumptions star. So remember, our varifold is the rectifiable set M and the density theta, stationary in U. So that'll always be assumed. But then, more importantly, we'll always assume that, without loss of generality, that 0 is in the support of mu. Just to have a definite center point to focus on. And also we'll assume that theta is bounded below by the number 1, almost everywhere. So here mu is just the mu sub v, which remember is just Hausdorff measure restricted to theta. So we'll assume that. And then the key assumption, by the way, remember from our discussion of monotonicity, as soon as theta is bigger than or equal to 1, almost everywhere, notice that then automatically the density theta mu y, that thing, which remember means the limit as rho goes down to 0 of mu p rho y over omega n rho to the n. Remember that by monotonicity that exists almost everywhere and is upper semi-continuous. That was one of the consequences of the monotonicity formula. So this is an upper semi-continuous function. If theta is bigger than or equal to 1 almost everywhere, that means this is bigger than or equal to 1 everywhere, for every y in the support of mu. So that's a useful fact, that if we assume, which we are doing, if we assume that theta is bigger than or equal to 1 almost everywhere, then actually the density is bigger than or equal to 1 at every point. So we're going to make use of that. And then comes the important assumption. Namely, we're at a point where the density is not too much bigger than 1. So we're assuming that theta n mu at 0 is less than or equal to 1 plus delta. And here delta is just, for the moment, a number between 0 and 1/4. We may want to assume it's small later, but for the moment it's just a small number between 0 and 1/4. So that's sort of the key assumption. That's the key hypothesis of the Allard theorem. What we ultimately want to prove then, which is the content of the Allard theorem, is that the support of mu is actually a smooth manifold in a neighborhood of 0. But obviously that's highly non-trivial fact, so we have to do some work to do that. Okay, so they'll be our assumptions. I'll keep referring to these assumptions. And the first lemma is the affine approximation lemma. Affine approximation lemma. So for this one, I've got to keep track of the constants. There's a lot of constants. So you probably won't notice most of them, but I don't want to get them wrong. So the affine approximation lemma, we're going to be assuming that delta is between 0 and 1/4. Oh yeah. Well, before I state the lemma, actually, I should do a little bit of preliminary computation involving this thing. So remember, this was a consequence of the monotonicity. So let's make another couple of remarks before I actually state this lemma. Let's make another couple of remarks about this. Remember the monotonicity identity. Was that the measure of B sigma centered at y over omega n sigma to the n minus the density mu y is equal to the integral over the ball of this non-negative term. You remember this non-negative term? It was r to the minus n times the projection onto the normal space, ptx per. So it's projection onto the normal space of x minus y over the length of x minus y. That's a unit vector squared. Squared d mu. And of course this is bigger than or equal to 0, which in particular means this is an increasing function. So we have that, and in our case, this is less than or equal to, well, theta is bigger than or equal to 1, but we're assuming that theta mu, the density at 0 is less than or equal to 1 plus delta. Oh, right, sorry. In fact, yeah, I do want to assume that, but that's not the way I want to state the hypothesis. I want to use the fact that if that's true, if theta n mu 0 is less than or equal to 1 plus delta, then in a suitably small ball, remember this is the limit of mu b sigma or b rho 0 over omega n rho to the n. So if that's, well, for example, if that was strictly less than 1 plus delta, then this converges to that, which is strictly less than 1 plus delta. So it'll mean that for suitably small rho, this quantity will be less than or equal to 1 plus delta. And that's the way I want to state this hypothesis. So rho is a given number. So B rho is a ball contained in U. And I'm assuming that B rho 0 over omega n rho to the n is less than or equal to 1 plus delta. Of course, it's bigger than or equal to 1 because we're assuming that density, we know that the density is bigger than or equal to 1 everywhere. So this would certainly say it's bigger than or equal to 1. This is bigger than or equal to 0. But now, what can we say now if we make this assumption? Well, as long as we keep sigma less than rho, then this will be less than 1 plus delta minus 1. So this will be less than delta. This difference will be less than delta. So we'll get, so that's nice. So we get that mu b sigma y over omega n sigma to the n is bigger than or equal to 1 and less than or equal to 1 plus delta for every y. So that'll be, now let's see. At the moment this, so I didn't quite say that correctly, did I? Because here we're talking about balls centered at the origin. Here we're talking about balls centered generally at a general point. So what can I say about that? Well, this is less than or equal to, let's see, as long as I have b sigma y, let's agree that we take y rather close to 0. So let's agree that y is in the ball of radius delta rho, centered at 0, and sigma is less than or equal to 1 minus delta rho. Then, in that case, you see by the triangle inequality, the ball of radius b1 minus, the ball b sigma centered at y is contained in the ball of radius rho, centered at 0. So therefore I can use the inclusion. So I get that this b sigma y is contained in b rho y, so this is less than or equal to, well, let's see. By monotonicity, this is certainly less than or equal to, so I've got to do a little bit of gymnastics here. I'm going to use the monotonicity of this quantity, and I'm going to take sigma, this is less than or equal to the ball of radius 1 minus delta rho with the same center. So this is less than or equal to the ball of radius 1 minus delta times rho, still centered at y, over omega n 1 minus delta rho to the n, as long as sigma is less than or equal to 1 minus delta y. That's true. And then also that will be less than or by inclusion. This will be, let's see, if y is in b delta rho, then by the triangle inequality, this ball will be contained in the ball of radius rho, centered at 0. So let's use that. So this is less than or equal to mu b rho 0 over omega n 1 minus delta to the n rho to the n. So let's summarize that. So I get that mu b rho y is bigger than or equal to 1 and less than or equal to mu b rho 0 over 1 omega n rho to the n times 1 over 1 minus delta to the n. As long as sigma is, as long as we respect this condition, sigma less than 1 minus delta times rho. So we have that, sigma less than or equal to 1 minus delta times rho. And that will be less than or equal to, well, we're assuming that's less than 1 plus delta. So this is less than or equal to 1 plus delta over 1 minus delta to the n, and of course that's less than or equal to 1 plus a constant times delta, where the constant just depends on n. Okay, so that's good. It means we've got very strict control on these density ratios as long as we stick to the stipulation that y should be in a small ball centered at 0, and sigma should be like that, less than or equal to 1 minus delta times rho. So let's continue that here. Thus, y in b delta rho 0 and sigma less than 1 minus delta times rho implies mu b sigma y over omega n sigma to the n is bigger than or equal to 1 and less than or equal to 1 plus c delta. So that's one nice inequality. The other nice thing is we can use the monotonicity again here on this ball. So we've just proved this is less than 1 plus constant times delta. So we'll get that this term then we're subtracting off something that's at least 1. So that this difference here, according to that, will be less than constant times delta. So this term must be less than a constant times delta. So we get integral b sigma y r to the minus n p tx perp x minus y over length of x minus y. So this is the orthogonal projection onto the normal space squared. That's less than or equal to c delta. And again, this is for sigma less than or equal to 1 minus delta times y. So we may as well just put that in. B 1 minus delta times rho centered at y. It's less than or equal to that. So these are the two inequalities that you get by doing a little bit of messing about with the monotonicity identity. You end up with these quantities here, which is sort of uniform. The nice thing about these is that they're uniform. This is, this is intersect support of mu, of course. This is all, remember, you only get density bigger than or equal to 1 if you're in the support of mu. So we definitely needed that we're in the support of mu. But the nice thing about these is that they're now uniformly true. In this small ball, centered at 0 in the support, and likewise this one also, uniformly small. So we've got those to work with. Now let me state the affine approximation lemma. So the affine approximation lemma says the following. If you take delta between, well, you've got to take delta a bit smaller, this is between 0 and 1/16. So far it was just less than a quarter. And these hypotheses, same hypotheses, and that means in particular we've got those things on the right board there, then you get a nice affine approximation result, namely that integral over b1, 0, integral over b delta y of the distance of x to is that for every, okay, so this is a statement, this is one of these uniform statements. For every sigma between 0 and 4, so you've got to get the constants right. For every sigma between 0 and 4 delta rho. So, in other words, sigma close to 0, less than a constant time, less than 4 delta. The 4 is not too significant, it's just that you've got to do that to make everything work out correctly. And for every y in the support of mu intersect the ball of radius delta, ball of radius 2 delta, centered at 0. Then you get the following. There exists an n-dimensional subspace depending on these values. So for each given y and for each given sigma in this range, you get the following. You get that the distance to the affine space, that's distance to y plus t. This is exactly the affine quantity that I was referring to, this thing. Y plus t squared. This is y plus t over sigma squared d mu is less than or equal to constant times delta to the 1 over 2n plus 2. Small in particular. So very nice result. It says that you can always make this quantity that appears on the right of this lemma that we were talking about, this height measure. You can always make this small. In fact, you can make it less than you can make it as small as you like, as long as you take these hypotheses with small enough delta. Now notice that's not at all obvious, because this hypothesis here, this is the main hypothesis, this doesn't give you any obvious way of choosing a direction for this n-dimensional subspace. And yet the claim is that there is always, for every scale sigma and for every point y, close enough to the origin, there is such a t. It depends on y and sigma, but nevertheless it exists, and it makes this quantity small. So I'll show you the proof of this after we take a little break. Oh yeah, it's the sigma to the minus n, of course. Everything's got to be scale invariant.
Sigma to the minus n.
Yeah.
Okay.
Yeah, that's right. And yeah, of course. Scale invariant quantity. Naturally. Oh, and I squared everything, so actually this is also wrong power. This is plus 1. When you take the square root, it's 1 over 2n plus 2. Yeah.
I was very impressed when you were doing this sigma delta on your feet like that. You delta under gamma. You know the picture, right? You know,
Yes.
this is small here and the
Yes.
and you end up with the,
Yeah. I forgot to prepare that really properly, so I took quite a long time doing that.
but you didn't obviously screw it up.
No.
Or at least you make it complicated enough so people can't pick up.
I didn't screw it up. Yeah. You know, we're going to have an open problem session on Wednesday, so if you've got any open problems, bring them along.
Well, did you hear what the Yng-Ing, I can't pronounce her name.
Ying.
Ying. You know what she said? When she talked, she's gradually building it up. She said, "You don't mind that we tape it."
Right.
Oh, you don't mind if we have a little introduction and discussion on each problem.
Right.
And you sign your life away. You don't mind that, do you? That you stand in front of the whole world.
Well, that's okay.
That's this question I got.
Yeah.
I mean, how difficult shall they be?
Right. Well, yeah. It's fine. It's fine if they're difficult. We don't have to solve them on the spot.
It's preferable that you don't, choose the open problem to be the theorem of your best friend, for instance.
Yeah, that's the other thing. I mean, if you have some secret open problems, you don't have to tell us. Well, I mean, if you've got a favorite one that you think you're making some progress on, then you obviously don't want to be talking about that at this point.
No, but
Actually, I will have a few open problems anyway in my talk already. So.
Okay, good. That's good.
So there are already
Good.
3 or more there.
Okay, great.
So.
Okay, so we'll get those.
But I live in fear of, saying this open problem and so forth, and somebody says, yeah, well, don't you know that that was solved like 12 years ago?
Right.
I think that happened when the Russian was still publishing, Russian people were still publishing in Russian. This was the danger, right?
Oh, yeah, of course. Well, sometimes Gromov would tell you it was solved when it wasn't always solved.
Right.
It was sort of...
Don't you love that?
Sort of standard comment,
Yeah.
Yeah. No, but it did certainly occur. particularly in the 70s, 80s or something, you know, when there was slowly more communication with,
So,
yeah.
I wonder, isn't the monotonicity identity, isn't there omega n to the minus 1 on the right?
Oh, yeah, there is, right, yeah, of course, yeah. Many other errors here as well, too.
Yeah.
I mean, it's a constant anyway, so.
Right, no, that's right, yeah. Of course, it's there.
I mean, it's tough to get through other 2 lectures. Do you
I've got 4 hours, 4 15-minute lectures, which is pretty hard. But this simplifies his proof somewhat, this affine approximation. This is not the way he does it.
No, he does it, well, I don't know why.
Using a variant of, he uses a variant of the monotonicity argument to get his Lipschitz approximation. I prefer this one, using this to get the Lipschitz.
Yeah, I'm not sure yet what to...
No, well, you'll see.
Yeah. So, I mean, it's more quantitative. I mean, the initial approximation by compactness is of course faster, but...
Yeah, but, I didn't want to do that, yeah, of course. Yeah. If you use the compactness theory and so on, I prefer to actually develop it sort of barehandedly.
Yeah. I mean, it gives you a sharper bound. You have to work a bit more, you get more. I mean, this is consistent.
Yep.
I think for video tabs, you could just keep it secret, and it's like just for record.
Yeah.
And make sure the statement
Right.
is correct.
Okay, right.
Reveal it, but shouldn't put it on the internet.
You mean charge money for it?
Oh, that's a good idea.
Put it on Amazon or something, you know?
So you're with videotaping the lecture, right?
No, we have to discuss. I think. But
well,
all the
but you
lectures, I don't think you said we videotape all the lectures, but just say open problem, right?
Yeah, I think so. Yeah, I think so.
How do you
So I
mean
think-
the conference?
Yes, conference.
Because whether you're not videotaping this today, you have already decided.
No, this one.
Yeah, no, they're videotaping this. All my errors will be
This one you can buy on
held in,
Amazon, right?
held in perpetuity.
Right.
I remember I did a conference in Grenoble, and they asked me before, like a few weeks before, you want to videotape, and I didn't know how much time I would have to prepare.
Right.
Oh,
Yeah.
no, I don't
it's safe.
videotape.
Right. That's
don't
the
know
wise
that.
choice.
And then in the end, I was sort of regretted it because I thought, okay, I had the time to deliver a proper lecture.
Right.
And
Yeah.
but I'm somehow, I don't know, I'm more used to the conventional
Yeah, sure.
form of publishing by writing,
Yeah.
not by talking.
Okay. Okay. Okay, so let's restart. So, couple of corrections. So I left off a sigma to the minus n here. Of course, this has to be scale invariant, otherwise it's meaningless, nonsensical. And also here, the correct power is 1 over n plus 1, not 1 over 2n plus 2. When we take the square root of that, we'll get 1 over 2n plus 2. So the power 1 over 2n plus 2 will crop up a bit as we go along. All right, and Ulrich also pointed out that I missed out the usual 1 over omega n factor here. Okay, so let's give the proof of this inequality. So we somehow have to cook up using this density fact, in particular using those inequalities on the right board there. We somehow have to cook up an affine approximation to this, which works in this sense. So let's do that. So, first thing to do is, this is all scale invariant the way it's written now, so we should rescale everything so that sigma becomes 1. So rescale, and at the same time we can also translate so that y goes to the origin. So let's do that. Sigma equals 1 and y is equal to 0. So let's assume those things are true. And now let's see what we can say. Well, we have these inequalities to work with. And when we rescale so that sigma becomes 1, we have, in fact, this would then be valid for any sigma less than 2 and bigger than 0 in the rescaled setting, and with the same constants. And likewise, this would be valid for, let's see, I think that's the unit ball. Yeah, let's take the unit ball there, the ball of radius 2. So after we rescale, we at least, in fact, we get a bit more if you take delta small enough. But you can certainly arrange these things. That this is true for sigma from 0 between 0 and 2, and this is true over the ball centered at y of radius 2. So we have those inequalities to work with, and right. So. Yes. So now, notice that this in particular, we can just throw a bit of information away here. That's r, so this becomes r to the 2 minus n bigger than or equal to 2. So this one in particular implies that integral over b2y of, just drop that term entirely. It's bigger than or equal to 1. So n is bigger than or equal to 2, so bigger than or equal to 1, and it's just this quantity, the txm perp of x minus y squared d mu is less than or equal to c delta, and that's for every y in the ball of radius 1 centered at the origin, intersect with the support of mu. So that's what things look like in the rescaled setting. In particular, you get this in the rescaled setting. Okay, so now we're going to take a covering now by balls. So I'm going to take a covering of support. So cover support mu intersect B10, the unit ball, by balls of radius delta to the alpha. Now we want to do that in an efficient way. So here's the picture. We're in the unit ball, radius 1, and we've got the support somewhere here, and we want to cover by balls of radius delta to the alpha. And we want to do that in a fairly efficient way. So in fact, let's choose a maximal collection a maximum pairwise disjoint collection of balls B of radius delta to the alpha over 2, centered at various points yj, j equals 1 up to n. So these are centered at points in the support. So yj, j equals 1 up to n in the support. Support mu. So that's the picture. Now, if you take a maximal pairwise disjoint collection of balls of radius delta over 2, maximal here just means maximum number, right? There's a finite number. So you just take the maximum number of balls that you can pick pairwise disjoint, like so, and that means that this then is contained in, automatically is contained in the union of the balls of twice the radius. So that's an efficient way to choose a covering by balls, yj. So you get a nice covering in that way. Now let's see if we can count the number of balls that you need to do that. So then the number of balls that you have, each ball has radius delta alpha over 2. So each of these balls has measure bigger than or equal to omega n times the radius to the nth power. So we get n times omega n times the radius to the nth power. The number of balls, that's less than or equal to the sum of the measures of the balls. From j equals 1 up to n of mu v delta to the alpha over 2, centered at yj. And that is these are disjoints, so that's less than the measure of the ball of radius 1, centered at 0, so that's less than or equal to constant c. So that's good. So we get that inequality. And so that means n is less than or equal to c. Notice I'm still sticking to the convention that c depends only on n and k. So less than or equal to c times delta to the minus alpha n. It's the number of balls that you need to make that cover. So that's an estimate on the number of balls. Now, on the other hand, so let's go back to this inequality. In this inequality, we can take yj, we can take y equals yj and sum each of these balls, notice, is contained in the ball of radius 3, centered at 0. For each yj, the yj's are in the ball of radius 1. So you get integral, so the sum, so I'm going to set y equals yj and I'm going to sum. J equals 1 up to n. Integral v2, yes, sorry, I should, v2, sorry, it's the other way around. I want to get a uniform bound. So I want to assert that this is, notice this contains the ball of radius 1 centered at the origin. Because yj, this is the ball of radius 2, and y is a point in the unit ball. So the ball of radius 1 centered at the origin is contained in the ball of radius 2 centered at y. So we get a uniform bound. And we're summing this term with y equals yj. Less than or equal to, and then less than or equal to, well, it's less than or equal to delta, but there are n terms, so it's less than or equal to c times the number of terms, which is less than, let's just write it as n, times delta, since each of these terms is less than delta. So this is less than or equal to c times delta to the 1 minus alpha n. So we get that. At the moment, alpha is arbitrary. I'm going to choose alpha in a minute. Alpha is between 0 and 1. Okay, so we have that, and then, yes, so, right, so that means that if you take any k, take k large, then this quantity has to be less than k. So I can put the sum inside, notice. So this tells us that this quantity must be, so if we take an arbitrary k bigger than 1, this quantity, j equals 1 up to n, p tx m perp of x minus y squared must be less than or equal to k times this, ck times this, except for a set of measure less than 1 over k, less than or equal to 1 over k. Because if you had the reverse inequality on a set of measure bigger than or equal to 1 over k, then of course that would contradict this inequality. So that's certainly a true statement. So, and now we've just got to decide what a good choice of k is. So let's take k to be, well, I want to be able to apply this. So this is true for many x, except for a set of measure less than or equal to 1 over k. So yeah, so let's choose, remember that we've got the measure of the ball of radius delta to the alpha centered at the origin over delta to the alpha to the n, omega n. That's bigger than or equal to 1. So that means the measure of this guy is bigger than or equal to omega n times delta to the alpha n. So we should pick k so that 1 over k less than this measure, omega n delta alpha n. So we could take it, for instance, k to be this over 2, for example. So let's do that. And then there'll certainly be points in x in this ball that satisfy this inequality. So then there exists an x in this ball, p delta to the alpha 0, with this inequality holding. Txm perp x minus yj squared less than or equal to ck. Now k is this, so this is delta to the, so it's delta to the 1 minus 2 alpha n. Now, yeah, so we got an extra delta to the minus alpha n from k, like so. So that's good because this is still small as long as we take alpha n less than 1. So we have that for some choice of x in this ball. Oh, sorry, intersect the support. Like so. And that's basically it then. If we call this, but maybe it's better to call this x0 to emphasize it's a particular point, x0. So that's actually that's actually the conclusion that we want, because in fact there's not much to this proof. It's just that you've got to make sure you read this off correctly now. So let's take a square root. C minus a half, delta to the half minus alpha n. and that, and then x0, this is x0. This is in the ball of radius delta to the alpha. So by the triangle inequality, that means that sum j equals 1 up to n of p t x0 m perp yj is less than or equal to c times delta to the half minus alpha n plus this x0 has got a distance to the origin less than delta to the alpha, so you get an extra delta to the alpha here. The alpha, right. And now we can choose alpha. So notice this is certainly bigger than or equal to the maximum. Maximum over j of each term. So you take the maximum of the terms, yj, less than or equal to that. And now we can choose alpha. Let's choose alpha so these two exponents are equal. So let's see, that's alpha equals a half minus alpha n. So that means alpha times 1 plus n equals a half. So alpha is 1 over 2n plus 2. 1 over 2n plus 2. So that means this is less than or equal to c times delta to the 1 over 2n plus 2. Okay, and yeah, so, right. So then, yeah, in fact, sorry, I actually, I'm going to prove much more than this. I'm actually going to prove that that it's really the actual height, the actual soup is less than this. So this is soup over x in b sigma y. Sorry, I got confused there. This is less than or equal to c, and now I've taken a square root, so we do get back to the 2n plus 2. So it's much better than just the integral being small. You actually get the soup being small, so we get that the soup is small. Now, this says that each of the points yj that we chose, now remember the picture was this. We had a ball of radius 1, we had a support here somewhere, and we're covering it by these balls centered at these points yj of radius delta to the alpha. So by definition, since they cover, that means each point in the set has got distance less than delta to the alpha to one of these yj's. So this tells us that soup over x in the ball of radius 1 intersects support mu of p t x0 m perp of x, that is less than or equal to c delta to the 1 over 2n plus 2. So indeed, we have exactly this inequality, but with soup. Sorry about that, I somehow got confused there. So that's the affine approximation lemma. There's actually not much to that, it's just a covering using the monotonicity. Okay, so now let's talk about the Lipschitz approximation. So we're going to make use of this affine approximation result to show that we can actually approximate the support by a Lipschitz function, the graph of a Lipschitz function. Okay, so let me Okay, so that's the Lipschitz approximation theorem. So let me state that theorem first. So still assuming star up there. Assume star. And this time, let's scale so that rho is equal to 1. It's convenient. And choose, let's let, so we're going to use this affine approximation result. So let's agree to let T0 be the choice of affine space that works here when y is equal to 0 and sigma is equal to 4 delta. So T0 equals T0 4 delta. And without loss of generality, we can of course assume that that's Rn times 0. So let's do that. So that's just a normalizing condition, since you can arrange that by rotation. Then, and let L be a given number between 0 and 1. Then the claim is that there exists a beta, positive number, just depending on n and k, between 0 and 1/4, such that, oh, and a delta, again small, so this time I want it to be between a 0 and 1/16. This is, you should sort of ignore these stipulations. They're just technicalities to make sure the details of the proof work out right. The main thing to keep in mind is that we're taking small choice of delta, by some fixed quantity. So we're assuming that hypothesis with small enough delta, and the claim is that you can find a Lipschitz graph and a Lipschitz map. From F, let's call it, from V delta 0, and this is the ball downstairs in Rn. This is the ball centered at the origin, downstairs in Rn. And this maps to Rk. Remember, everything's happening in Rn plus k here. So the claim is you can find a Lipschitz map with lip F less than or equal to this prescribed number L, and with and also a bound on the soup. A bound on the soup similar to this, like so, and soup mod F less than or equal to C times delta to the 1/2n plus 2. And the claim is that you can do that in such a way that F approximates the support. So in other words, delta to the minus n, this is all happening on the ball of radius delta. So this is mu of B delta 0. So we're looking in the ball of radius delta 0. The n plus k ball of radius delta centered at 0, and we're taking the intersection of that with the support of mu minus the graph of F. The claim is you can make that small. So in other words, graph of F chews up most of the support in this ball of radius delta. Notice, of course, this factor has to be here. That's the natural scaling factor here. And not only that, but you can also do this in the way that the support also chews up most of the graph. So in other words, you get an extra term here, namely delta to the minus n times the n-dimensional Hausdorff measure of the graph of F. A graph of F intersect B delta 0 minus the support of mu. And you can make that small. In particular, you can make it less than a constant times L to the minus 2. So the claim is that you can make that small, less than a constant, times L to the minus 2 times the tilt excess. So that's delta to the minus n integral B delta 0 PTXM minus PT0. Let's agree that T0 is, oh, here we are, it is T0. So it's Rn cross 0 squared T mu. And that, in turn, is less than or equal to a constant times L to the minus 2 times delta to the 1 over n plus 1. Notice this holds because of the, remember we already proved this, that the tilde excess is always bounded in terms of the height. And the height here is, remember we proved that the height can be bounded even in soup by C delta to the 1 over 2n plus 2. So this is already established, this one. That's no problem. The main content is that you can prove that you can find a Lipschitz graph so that that graph chews up most of the support, and conversely, most of the graph is chewed up by the support, to the extent that what's left is just a multiple of the tilde excess. So notice that that's sort of a negative. That it says that if you try to do this with a small Lipschitz constant, then you have to pay for that. You can do it, but you have to pay for it by having a negative power of the Lipschitz constant. This is, in any case, small. It's less than delta to the 1 over n plus 1 by our discussion before the break. But so that's good. But on the other hand, you can't take L2 small. If you take L2 small, it'll wash out that small factor and you'll get no very useful conclusion. You'll just get a large number here instead of a small number. So this is a negative, but it's not too negative. For instance, you might be happy taking L equals 1, for example, in which case there's no L there. It's simply this, which is small. So that would be good. Okay, so let's give the proof of this. Proof involves using the affine approximation result. So proof. Well, you're going to break everything up into a good set and a bad set. This is sort of a typical classical analysis result where you divide sets up into good and bad sets. You've got to find the sets appropriately, and then use covering lemmas in order to conclude what you want. So let me break it up as follows. To find a good set, namely G is going to be the set of X in the support intersect the ball of radius 2 delta. And again, don't worry too much about these constants. The main thing is it's a ball of radius roughly delta. It's for technical reasons you take 2 delta, but that's not so important. Such that the following is true. Namely, sup over sigma between 0 and delta of the tilde excess V sigma y. Oh, this is the set of y, sorry. V sigma y of PTXM, orthogonal projection of TXM, minus T0 squared T mu is less than or equal to beta squared L squared. And here beta is a small constant to be chosen. It's the constant that appears in...
Sorry, but
yes.
there seems to be a delta role of the delta. In star there's already delta, so it's in the hypothesis, and the conclusion exists also delta.
Oh, sorry. Yeah, sorry. This is supposed to say star, assume star, which is this guy. So that's where delta comes in. Yeah, just here, just there. And then the conclusions of this. Thanks. Yeah.
Only for this
Yes. No, well, in the rescaled setting, yes. R equals 1. So you're making delta small enough, and the claim is that you can correspondingly find a Lipschitz function of radius delta. So it does depend on that, yes. You apparently don't like that very much.
Well, it confused me. With
Yeah.
also the soup. So this is a function.
This is, yeah, I'm sorry, this is soup over delta. Yeah, of course, it has to be the scaled soup. Yeah, of course, this has to be the scaled soup, otherwise it's meaningless. Okay, so let's see here. So, so this is our good set. Beta is going to be chosen, so beta's this constant that we haven't chosen yet, 0 1/4, for the moment arbitrary. Take this. So that's the good set. So stare at that for a minute. That means when you're in the good set, this constant direction, T0, which we're assuming is Rn cross 0, works uniformly in the interval 0 delta. So it works for all possible sigmas between 0 and delta. Now, at this stage, it's not at all clear that that mightn't be the empty set, for example. We don't know how big this set is. So the claim is that actually it chews up quite a bit. In fact, the claim is that if you use G here, you will chew up most of the support, but we have to establish that. So let's do that. So let's think about what happens if you're not in this support. So Y not in G, Y in B2 delta 0 intersect support minus G. Then there will be some sigma between 0 and delta where the reverse inequality holds. So this sigma between 0 and delta with sigma to the minus n integral b sigma y p txm minus pt0 squared is bigger than beta squared L squared. So we would get that reverse inequality. And then we should think about using a covering lemma to see what we can say about that set. We want that set to be small because we want the good set to be most of support mu. So we'd like to prove that that the complement of G is small. So that's our aim. So so we can use 5 times covering lemma here. So we've got this set is covered by these balls, B sigma, or of this radius sigma. Notice the sigma that you get in each case depends on Y. So pick, so 5 times covering lemma implies that we can pick pairwise disjoint the sigma j yj with yj in this bad set G and pairwise disjoint and the union of the whole set, the bad set, is contained in the union of the 5 times enlargements of these balls. So we get 5 times sigma j centered at yj, union over j. So according to the 5 times covering, that's right. And then we can use these inequalities here. So I want to put the sigma onto this side. and takes sigma j, so this becomes a yj instead of a y. This becomes a sigma j. That becomes a yj. And this sigma j to the n, and remember that's bigger than a constant by monotonicity times the measure of the ball. So beta squared L squared times the measure of the ball of radius sigma j centered at yj. So we get those inequalities for j equals 1, 2, etc. from these guys. And so we should sum over j here. These are disjoint balls. On the other hand, I could make this 5 sigma j here. No problem, as long as I remember that the ball of radius, see there's a proportionality here. It doesn't matter much which radius you use, there's still a proportionality. So if I replace that sigma j by 5 sigma j, I'll be out by at most a factor 5 to the n. So we do that. So we get, these are now the balls of radius 5 sigma j, and these are the disjoint balls of radius sigma j. So now let's just sum. We've got this that's contained in the union of the 5 balls, so we get the measure of the ball of radius 2 delta intersect support minus g is less than or equal to the sum of the measures of these, which is less than, we've got to put these constants onto the other side, so that's less than a constant, times beta to the minus 2 times L to the minus 2 times the sum of these. The sigma j yj ptx m minus pt0 squared. And of course that's less than or equal to the sum, these are disjoint balls, so this is less than the integral over the b to the minus 2 L to the minus 2 times the integral over b. Now these balls are all contained in the ball of radius 2, I guess, centered at the origin. A ball of radius 2 delta. See, the sigma j's are in 0 delta, that's right. Ball of radius 2 delta centered at the origin, ptxm minus pt0 squared, d mu. And that is exactly part of the result that we wanted, because we've got a factor L to the minus 2. We haven't yet chosen beta, but we haven't needed to so far. We get an L to the minus 2, and we've got this tilde excess, putting it delta to the minus n on each side. So we should do that. Delta to the minus n, minus n, delta to the minus n. And this is exactly the term that we wanted on the right there, so that's good. And so that's at least this part of the thing taken care of. This bit I won't do. It's a similar argument. You'll find it in the text. It's maybe even a little easier than the argument that we just gave. So I'll leave that. I'll leave you to read up on this bit because I want to finish this today. So we've got this. It's less than that. But what we haven't proved yet is that we haven't yet got our Lipschitz function. So all we've proved is that this good set chews up. I haven't proved this, I've actually proved that. So what I'd like to do now is to show that G is indeed contained in the graph of a Lipschitz function. And that will do the job. So let's do that. So claim yes. What did you want here? I can get it back for you. Right. Okay. Bit late now. Yeah. So claim G is contained in the graph of a Lipschitz function. So let's check that. Okay, so yeah, this is actually not too difficult. So take any y1, y2, and g, and notice, and let's let sigma be the distance between them. There's G up there. It's a good set. Let sigma be the distance between them. So that's less than or equal to 4 delta, because each of them is in the ball of radius 2 delta. So that's less than or equal to 4 delta, that distance between. Each of them is in the ball of radius 2 delta, centered at the origin. So we have that. And notice that by definition of good sets, sigma to the minus n, integral b sigma over 4. Now this is one case where you've got to be careful about the constants. Ptxm minus pt0 squared d mu. I claim that's less than or equal to 4 to the n times beta squared L squared. Well, that follows from here. But notice, in order to apply this, you have to be in the good set. Well, that's good. We're in the good set. That's okay. But you've got to know that sigma is less than or equal to delta, and sigma is less than or equal to 4 delta. So that explains the sigma over 4 there, right? We've got to reduce that. And then this factor out the front is wrong. It should be sigma over 4 to the minus n. So you get a 4 to the n. So that's just being in the good set guarantees that. Now also by the affine approximation theorem, the affine approximation theorem implies that sigma to the minus n integral b sigma over 4, same ball. Oh, this is centered at y1. Sorry, we're at the point y, so I'm centering this at y1. I'll worry about y2 in a minute. B sigma over 4 y1, again, same thing, same domain. And now I'll take ptxm minus p, and instead of taking pt0, I take the affine space that we got in this affine approximation theorem. The affine space you get in this theorem depends on both the point you're at, which in this case is y1, and the radius, which in this case is this sigma. So we get p y1 sigma squared is less than or equal to constant times 1 over delta to the 1 over n plus 1. Notice it's not 2n plus 2 now because we're squaring this. So we get c times delta to the 1 over 2n plus 1. And, oh, I forgot to say in the statement, I should have said this, that we also agree ultimately to choose beta so that delta and beta star holds with rho equals 1 and delta less than or equal to beta L to the 2n plus 2. Star should hold with, notice this constant beta that we're eventually going to get only depends on n and k, so that all makes sense. So that means that this is less than or equal to c beta squared times L squared, because delta to the n plus 1, delta to the 1 over n plus 1 is less than beta squared times L squared. So we have that. So we've got these two inequalities. And that's good because we can just use the triangle inequality or the squared triangle inequality if you want to be picky about it. And these are over the same domain, so you can just use the triangle inequality and you get that P these are constants, notice, they don't depend on x. This is d mu x. The integration in both of these is with respect to x. These are constants. So we get that using the squared triangle inequality, which notice involves a factor of 2, but that's okay, we get pty1 sigma minus pt0 squared is less than or equal to constant times beta squared times L squared. And that's good because now you see this is right. Well, yeah, the integration cancels out. We see the ball has got measure sigma to the n. That cancels out. So there's no integration left now. It's just a new constant. Yeah. Yeah. So now let's look at, so we get that. Now, on the other hand, so let's look at pt0 perp of y1 minus y2. Let's look at the absolute value of that. No, I don't think I want to write it down for y2 yet. No, I think it's okay just to use y1 here. And that's equals pty1 sigma perp plus, I'm going to play a game with these quantities. So now I've made a mistake, so I've got to correct it by putting the difference between that and that in there. So pt0 perp minus pty1 sigma perp hitting y1 minus y2. And that's less than or equal to that plus that. Now this guy is, this was y1 minus y2. Now this guy by definition is less than delta to the 1 over n plus 1, right? Constant times delta to the 1 over n plus 1. That's the affine approximation theorem. So this guy is less than delta to the 1 over n plus 1. This guy is the difference between the orthogonal, in the projections into the orthogonal complements. But of course that's the same as the difference between the projections. So you can just erase the perps there. That's just trivially the case because the projection into the orthogonal complement is the identity minus the projection into the subspace. So that's the same. When you're taking differences, that's the same. And then we can use this here. So this is less than C beta L. So this is less than or equal to C delta to the 1 over n plus beta L mod y1 minus y2. Or, oh, I forgot the factor of sigma here. This is y1 minus y2, which is sigma. And if you stare at that long enough, you see that says exactly that G is the graph of a Lipschitz function. As long as you take beta small enough so that this constant is less than a half. See, this is, sigma is mod y1 minus y2. And likewise here, mod y1 minus y2. So this is less than or equal to, remember this is also less than C beta. I somehow erased that. No, I didn't. It's up here somewhere. Maybe it's here. Here. Delta is less than, delta to the 1 over n plus 1 is less than beta L squared. So all of this is less than C beta L sigma, like so. And that's C beta L mod y1 minus y2, like so. And this is the orthogonal projection onto the normal space, y1 minus y2. And so now let's let capital P be pt0 perp, and capital Q be the projection onto Rn. So the sum of those is the identity. And this says that capital P of y1 minus y2 is less than or equal to C beta L times capital P of y1 minus y2 plus capital Q y1 minus y2. Because P plus Q is the identity, so I just use the triangle inequality there. Q. So we just have to take C beta L less than a half, and we can pull this back on the left. So choose beta so that C beta L is less than or equal to a half. Then you get a half P y1 minus y2 is less than or equal to C beta L times Q y1 minus y2. And that says exactly that it's the graph of a Lipschitz function with Lipschitz constant less than 2c. Notice we can put the 2 over to here. So it's got a Lipschitz constant less than 2c beta. So we can certainly make the Lipschitz constant less than L if we just take that to be less than or equal to 1. So that's it. We proved that indeed the good set is indeed the graph of a Lipschitz function. Okay, so the remainder of the proof involves harmonic approximation using this Lipschitz approximation. So I'm going to talk about that on Friday.